Hello, calculus classes. This is for week number 3. We are talking about optimization. We did this, I'm guessing January, February, but if you remember, it was kind of a struggle. There were pretty much all story problems, and the hardest part was writing the equation, because you were really not given an equation. You were given a situation. So, I just wanted to help you set it up, because that was the hardest part, setting up the equation, at least getting to a point where you can get the equation. When we talked about this optimization, I always told you, focus in on the question. That's going to tell you what you need to solve for and what the equation needs to be. So, for number 1 on the 2 problems that I'm asking you to do this week, for the first part of the week, it says what, you got the sheet there, it's talking about a supermarket, taking basically a cardboard that's 14 by 30 inches, cutting some corners out of it, folding up the tabs to make a box. But the question says, what size should the squares be in order to create a box with the largest possible volume? So, we are trying to maximize the volume. All right. The thing that you're trying to maximize or minimize, that becomes your main equation. We want a volume, but it's going to be of a box. So, volume of a box, length times width times height. There's our main equation. But when we did this optimization, we only knew how to take a derivative with one variable. We have 3, length, width, height. Okay, what size should the squares be? So, in this picture, you are cutting out this square. It's a square. So we're going to call this x, because that's what we're really trying to solve for. What is that number? But it's a square, so we're going to cut out an x there, 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 and there. You get the idea. Okay, when we cut out all these squares, what we're going to do is, along these red dashed lines, we're going to fold these sides up, and that becomes the box. Okay. So, this whole length, from here to there, that's 30. We took out this x. Over here we took out this x. So this, we'll call this the length. It was 30, but we took out, that's a 0, but we took out 2 x's. Same idea here. Going from top to bottom, this was 14, but we took out that x, and we took out this x. So we'll call this the width. It was 14, we took out 1x, took out another x. When we fold along these red dashed lines here, this x became the height. Okay. We are trying to find the largest volume. So, the volume is the equation that we are going to take the derivative of. We have an equation for length. Start writing the equation. Volume equals the length, 30 minus 2x. I gave you the idea for the width. It was 14 all the way across. We took out 1x, we took out another x. The height is x. Now you've got an equation with one variable. We are trying to find the largest. So when we talk about finding a maximum, it's the same thing for a minimum. But when we talk about finding those things, you take your derivative, you test your endpoints, you test your critical numbers. Remember, critical numbers happen when you set the derivative equal to 0 or where the derivative is undefined. So, we got critical numbers, whatever those end up being. You've got your endpoints. So let's talk about the endpoints in this. It's going to change. Basically, we're talking about like the restrictions. What is the most x could be? What's the least x could be? We're talking about those restrictions. That is going to change for every single problem. So you really have to do a lot of thinking. With this problem, x is that square that we're cutting out of each corner. But we're cutting out 2 x's all the way across. So we could cut out to 15, but really we'd be cutting this whole thing in half. We don't want to do that. Could you cut out 15 going this way? Not so much. There's an upper limit to what you would cut. Okay, you don't want to cut halfway across either, so half of that. there becomes your endpoint. And you have to form a box. So the minimum you can cut out is, I guess, technically 0, but not really. So it's kind of like a starting point. We're not going to have an answer at 0. We're not going to have an answer at our upper boundary, because basically what this is just cutting this whole cardboard in half. It's not going to form a box, but it gives us some endpoints to maybe eliminate some critical numbers. All right. Oops. Get your equation, take the derivative, set that derivative equal to 0 to find your critical numbers, and so on. For the second problem, it's actually question number 3, but it says where should these, so what you got here is you got a 16-foot pole, a 24-foot pole. They're trying to tie them together, put these brace cables, guy wires is the proper name, at one point so that the top of this pole is attached to that one point, top of this pole is attached to that one point. What you do know is they're 30 feet across. All right, so where should the stake be placed? That's this point right here. That's the stake. To use the least amount of rope. All right, we've got rope here, and we've got rope here. So we want the least amount of rope. So that is going to be a distance. All right, the only thing we know is it's 30 feet all the way across. I'm going to call this X. Okay, we don't know this point, this where the stake is going is in the middle. It could be anywhere. That stake could be right here. It could be anywhere over here. Basically anywhere in this 30. But we needed length for this rope, and we need something for the length of this rope, because that's what we were trying to find the least amount of. So we don't know where this stake is, so I'm just going to call this one X. To find this length of rope, it's a right triangle. Do some Pythagorean theorem, you're going to get an expression for this length. Now, if this length is X, this length right here has got to be whatever the remaining part is. So it was all 30, take away that X. Again, here's a different right triangle. So you do Pythagorean theorem with this one, and I'm going to help you set this one up. So I'm going to call this length 2. Okay, length 2, let's go down here. Length 2. It's a Pythagorean theorem. So I'm going to square that length, that's the hypotenuse squared, to equal one leg squared plus the other leg, which is 24 squared. All right, I just want the length. I don't want the length squared. So I got to take the square root. So the length of that rope, L2, is the square root of all this. 30 minus X quantity squared plus 24 squared. Okay. Where should the stake be placed to use the least amount of rope? Length 1. That was for this rope. Again, Pythagorean theorem to get an expression for that. Plus length 2. I gave you length 2. There's your total distance of rope. We want to find the minimum amount. So, minimums. Take the derivative. Set that derivative equal to 0. Find your critical numbers. Your endpoints, well, your endpoints, technically there could be a lot. The endpoints are kind of weird in this situation. Technically, you could tie this one this rope all the way down here, but then you wouldn't have anything to tie it to there. So the endpoints aren't really going to be a good answer, but your critical numbers are. I hope that helps you. Good luck. Let me know if you have questions. Send me an email. Not that I'm asking for people to call during office hours, but I got a grand total of 0 so far in these 4. I hope everybody's doing well. Take care.